Radiative cooling is a way to cool without using any electricity. We would like to tell you about the experiment which we have done in this field and its results. First, let's talk about the motivation to study the idea of radiative cooling. Cooling systems today represent a considerable fraction of the total energy consumption in the world. This trend is expected to grow due to climate change, population increase, income growth, and potential technological improvements. The most common energy-consuming cooling systems are air conditioners, commercial refrigerators, and data centers. Currently, the percentage of households equipped with AC in selected countries, such as Brazil and India, is very low, but it is expected to drastically rise in the future. It is predicted that the cooling energy demand in the residential sector alone will increase by up to 750% in the next 30 years. If so, creating more efficient cooling systems might have a huge impact on our energy consumption. To explain a technology that exists today, we must first explain some concepts in physics. Radiative cooling is a process in which a body loses heat by black body radiation. So what is black body radiation? Every body emits energy as a light wave. The frequency of the light is determined by the temperature of the body. This phenomenon is called black body radiation. Using this principle, we can measure the temperature of objects as displayed in these thermal images. As we can see in this graph, which shows the atmospheric transmittance percentage as function of the wavelength, our atmosphere either absorbs, reflects, or transmits light depending on its frequency. As you can observe, our atmosphere has a transmittance window in the wavelengths ranging from 8 to 13 microns. This transmittance window is known as the atmospheric window, and it allows us to cool certain objects by releasing their black body radiation into outer space.
Another term which we will use in this video is the air mass coefficient. The air mass coefficient is a distance unit where a single unit is measured as the distance between the Earth's surface and the atmosphere's edge in the zenith direction. For example, if a light ray is directed at 45 degrees from the zenith direction, we will have an air mass coefficient of approximately 1.5. This is relevant for us since the atmosphere's transmittance is dependent on the air mass coefficient. In the displayed graph, we can see that the transmittance of the atmosphere is a function of both wavelength and air mass. We can see that for air mass equals 1, the atmosphere's transparency is maximal. So, how do we calculate the net cooling power of a system? The net cooling power is calculated as the radiative power emitted by our emitter, from which we will subtract the power which enters our system by the means of conduction and convection, and the radiation absorbed from the sun and the atmosphere. In our experiments, we will try to maximize the net cooling power by minimizing the absorbed radiation from the atmosphere. The field of radiative cooling has been researched for over a decade at this point. The most notable advances in this field have been research and development of selective emitters, which are black body emitters who emit and absorb radiation mainly inside the atmospheric window, thus allowing radiative cooling to occur while placed under direct sunlight. A team in Stanford has used such materials and a vacuum chamber to reach 42 degrees Celsius below ambient temperature using the display design. We are finally ready to talk about our research. Given an emitter, what will be the best geometry to maximize the system's cooling power? For the baseline system, we have chosen a square plate with walls angled at 45 degrees and covered with aluminum foil. This is done in order to limit the incoming atmospheric radiation to an air mass coefficient of up to 1.5. For the second system, we have chosen a parabola covered with aluminum foil, with the emitter placed at its focus. This design was chosen because of the parabola's specific characteristic that every ray emitted from the parabola's focus will reflect from the parabola to the zenith direction. Again, this allows us to minimize the radiation absorbed by the system, since we limit the incoming radiation angle to approximately 0, whose air mass coefficient is 1. For the third system, we have chosen a half ellipse covered with aluminum foil and mylar foil, with the emitter placed at its focus. This design was chosen because of the ellipse's characteristic that every ray emitted from one of the focuses will reflect from the ellipse's surface to the other focus, thus allowing only near zenith direction rays to be emitted and absorbed, while decreasing the system span in comparison to that of the parabola. Each system was insulated with a thick layer of styrofoam from each side except for the side facing up to reduce heat conduction, and covered with aluminum foil from every side to prevent heat transference via radiation, as aluminum is a very good reflector for all wavelengths. The systems were sealed from the top with a thin layer of polyethylene to reduce heat convection, due to the fact that polyethylene is mostly transparent in the wavelengths at the atmospheric window. Each system's temperature was taken under the emitter surface, and each system's emitter has the same surface area. The chosen emitter for this experiment was O-proof foil, which is a decent selective emitter. The experiments took place simultaneously on a clear, dry winter night. Okay, now let's move on to our results. These are our preliminary results for the first experiment. We can see the temperature as function of time. On the left, we can see the results for the daytime experiment, and on the right, the nighttime experiment. The purple line represents the ambient temperature. The green line represents the baseline design. The red line represents the parabola design, and the blue line represents the ellipse design. In the daytime experiment, we can see that the parabola and the ellipse performed roughly the same and were colder than the plane by about 2 degrees Celsius. The spike in the parabola performance is due to the system falling down from a strong gust. In the nighttime experiment, we can see that the half ellipse and the baseline performed roughly the same, while the parabola design was at all times about 2 degrees colder. Also, at peak performance, the parabola reached about 20 degrees Celsius below ambient, although this experiment might have had a sensor calibration problem. As seen in the results of the nighttime experiment, the parabola performed better than the baseline and the ellipse. We believe that the ellipse may have performed poorly because of the extra layer of mylar. In the daytime experiment, we've seen that the parabola and the ellipse performed roughly the same and were both better than the plane. We believe that the emitters absorbed some of the solar radiation and thus were affected according to each design's span. Since the ellipse had the smallest span, it absorbed less solar radiation and performed as well as the parabola while still having the mylar layer. We also believe that both the half ellipse and the parabola can perform much better. Since the emitter's radius is relatively big in contrast to the shapes, we believe most of the emitted radiation from the bottom part of the emitter gets reflected back and then absorbed by the emitter, thus reducing significantly the effective emission. We believe that by raising the focus higher and changing the shape of the designs directly below the emitter, we can make the effective emission much higher, thus making both designs significantly better than the baseline. Thank you for watching our video. Leave a comment if you have a question or remark.